Hello everyone, welcome to what will be our pre-lecture for lecture number 25 here. We're going to talk about some basically applications of redox reactions. And so something that we covered before break nominally, but I feel like it's worth reviewing, is what a voltaic or a galvanic cell is. And so those two words are interchangeable, they mean the same thing. And it is essentially an electrochemical cell where we have a redox reaction taking place, separated into two different cells. We have an anode that is where oxidation is going to take place. And so our electrons are going to flow through some sort of circuit to our cathode where reduction will then take place. And so in this example, we have some metal cathodes. Because electrons have a negative charge and they're going one way, we need to balance that charge, and that is the purpose of the salt bridge here, where we have some sort of supporting electrolyte, so sodium and nitrate in this case, and they are going to flow in directions that help us balance the charge of our electrons. So for example, because negative electrons flow this way, sodium follows those, and then nitrate, the negative thing, is going to be repelled by them. Okay. And so, like I said, we have basically our reduction and oxidation reactions that we practiced last class. They're going to be taking place in the separate cells. So our anode will be where oxidation occurs. Our cathode will be where reduction occurs. Okay. And here's another kind of more anthropomorphized version of that figure, if that is helpful to you. And shout out to Diflorine on Twitter, who made this. So the opposite of a voltaic or a galvanic cell, so we have basically another representation yet of this voltaic cell shown here. If we were to reverse our polarity, so instead of electrons flowing basically from the zinc side to the copper side, if we hook up an external power source, so in this case another battery, and reverse the polarity there, we're going to push electrons back the opposite way. And so this is just the reverse chemical reaction. Something I'll point out here, and we'll talk a little bit more in the pre-lecture video and in class, is when we have a spontaneous or a favorable voltaic cell, we're going to have a positive potential. So this would be 1.1 volts. And then if we reverse our potential here, where we have electrons flowing the opposite way, that would then mean that we have a voltage source that is negative 1.1 volts or greater to encourage that reverse reaction to occur. Okay? And again, in case I have not defined that, when we go the opposite way, the unfavorable way, we would call that an electrolytic cell. Okay? So all of this has been basically measured. We've measured different types of redox reactions, and we have tables. There's a table that I'll talk about here in a moment, but we should be able to calculate the potential, so that's what E cell is, of any electrochemical cell by taking the reduction potential of the cathode and subtracting the reduction potential of the anode. And you might be wondering, how do we actually measure these values? Everything is referenced to the standard hydrogen electrode, which is shown here, where we have H2 gas, we have a platinum wire, and then we have a 1 molar acid solution. At our platinum electrode, we can interchange between H plus and H2 just through the movement of electrons, and at 1 molar concentration and 1 bar, or 1 ATM rather, of H2, our potential is exactly 0. And so everything is referenced to that potential. Okay? And so if we were to hook up the standard hydrogen electrode to any other half cell, so we call this a half cell because this is going to be where either reduction or oxidation takes place, because our electrons flow this way. We know this is going to be our cathode, so we're going to have reduction here. And so we can measure what that electrochemical half cell is relative to our standard hydrogen electrode. Okay? And so when we do this, we get tables. This is an example of two of the pieces of the tables here. Put this big red line here to indicate this jump. So you'll see that basically the most oxidizing thing we have on our table is going to be fluorine gas, and things that are very oxidizing have very positive potentials. The thing that is most reducing in this table is going to be lithium, and so it is going to have the most negative reduction potential. And so, like I said, more oxidizing potentials is more positive, more reducing potentials are more negative. Okay? And basically these things that have a very positive potential are going to be very easily reduced, whereas these things with very low potentials are going to be very difficult to reduce, and then vice versa for fluorine is then very difficult to oxidize, and lithium is very difficult to reduce, right? So everything kind of, or very easy to oxidize. So we can interchange that language, okay? And so questions that we'll be focusing on in class, / you've already had some experience with in lab, is say we made an electrochemical cell of silver and barium, and I would ask you what is oxidized and what is reduced. And so we would want to find those potentials. And so we have silver here, we have barium here. Both of these are written as reduction potentials, as is everything in this table. You'll notice that our electrons are always on our reactant side, because it is a reduction, half reaction. And so basically the way we would solve this is that because silver is more positive, meaning more favorable for reduction, barium is going to be the thing that is oxidized. So the more negative thing is going to be oxidized. And the easiest way to calculate this, in my mind, is to do E cell is the reduction potential at our cathode minus the reduction potential at our anode. So basically when you do this method, you don't have to change any of these values in the table. So you'll notice I plugged in this 0.7996 and I plugged in this minus 2.912, and I just subtract them. If you wanted to, like you did in lab, you could flip this reaction. When you reverse the reaction, you would also change the sign to make this positive 9.12. If you do that, this negative sign just needs to turn into a positive sign, where E cathode would be the same, but then it would be plus E anode. We could also say E red plus E ox, okay? And either way, we should end up with the same answer of this 3.7116 volts. And a reminder that E cell is always going to be positive for something that is spontaneous. Spontaneous is another way to say favorable, so something that will generate electrical potential for us. And finally, one other note is you do not need to multiply these reduction potential values, even if a reaction is multiplied by some sort of coefficient to balance the number of electrons. And so, for example, here, silver, we're only transferring 1 electron. Barium, we're transferring 2 electrons. So in order to balance this electrochemical reaction, we would need to multiply everything in the silver equation by 2. We would do that to balance it, but that won't actually change the potential for our cell. Okay? All right, that's it for the pre-lecture. Hope it was useful. If you do have any questions, please let me know. Otherwise, I will see you in class.